Greetings of the day to all of you. In today's lecture, we are going to discuss about harmonic analysis of PWM techniques. I will write here harmonic analysis of pulse width modulation, that's PWM techniques. And in this harmonic analysis of PWM techniques, we will primarily discuss analysis of line current ripple. I will write here analysis of line current ripple. As you already know, in our series of lectures in module 4, we have mostly discussed, and in module 3 also, we have discussed various types of PWM techniques. We have discussed sine triangle comparison based PWM technique. We have discussed third harmonic injection PWM technique. We have discussed various types of bus clamping techniques using triangle comparison PWM. Then we have discussed conventional space vector pulse width modulation technique. And we have also discussed how this space vector PWM technique can be implemented using triangle comparison by generating a proper, common mode signal and injecting that common mode signal, adding that common mode signal with 3 sinusoidal modulating waves. We have also studied space vector based continual clamp PWM, split clamp PWM, 60-degree clamp PWM, which is a special case of continual clamp PWM, 30-degree clamp PWM, which is also a special case of split clamp PWM. And finally, in last couple of lectures, we have been discussing about advanced, bus clamping techniques like advanced continual clamp PWM, advanced split clamp PWM techniques using double switching sequence, PWM. Right? So that means in module 3 and module 4, we have been mostly discussing about the types of pulse width modulation techniques, whether it is triangle comparison based PWM techniques or it is space vector based PWM techniques, what actually those PWM techniques are, how are they implemented, okay? How is, for example, bus clamping, exercised in triangle comparison PWM techniques? How is bus clamping exercised in space vector based approach? That was our main topic of discussion. That is, we were discussing about how to apply or how to implement various types of PWM techniques. Having understood various types of pulse width modulation techniques and how to apply them, now it is time to analyze these PWM techniques. Because the question is, why did we study these PWM techniques? Without analysis of these PWM techniques, it's useless, okay? Just studying PWM techniques for the sake of studying means nothing. When you study a PWM technique, then you must, after studying, after understanding it, you must do the harmonic analysis of this PWM technique. And you must compare this PWM technique with other types of PWM techniques which are reported in the literature. And then and only then you will be able to apply a proper type of PWM technique for your application. Your application may be, control of induction motor drive or maybe control of any other drive, right? So therefore, from in this lecture and maybe in next 3 to 4 lectures, we'll be discussing following topics. First of all, I will discuss with you briefly a review of PWM techniques. I mean various PWM techniques which we have already studied over last more than 10 lectures. We will perform a review of those PWM techniques. Okay, that will be followed by maximum fundamental output voltage of inverter. We'll try to see So since we have studied various types of PWM techniques, we will see what type of PWM technique produces how much of maximum fundamental output voltage. In other words, we will try to see DC bus utilization. We will try to study briefly about DC bus utilization of various PWM techniques, which we have already studied. It will be just a review of that. That will be followed by harmonic analysis. We will be drawing harmonic spectra. Harmonic spectra produced by different types of PWM techniques. And this harmonic spectrum or harmonic spectra will be understood by us only if we are able to develop the harmonic model of an induction motor. IM means induction motor. We will try to develop harmonic model of an induction motor, and we will try to understand these harmonic spectra which are produced by different types of PWM techniques when these PWM techniques are used to feed a three-phase induction motor. Once we know the harmonic model of an induction motor, we can find total harmonic distortion of current, and we can also find weighted THD, WTHD, weighted THD. What is this weighted THD? I will come to that in a minute's time. Then we will try to understand error voltage vector. Okay, error voltage vector means, for example, we have some desired voltage vector. Say, for example, this may be our desired voltage vector which we want to apply across our motor, across our load. Now this vector basically is a vector in alpha beta plane. Transforming it into ABC plane, it represents three-phase voltage. Okay, this three-phase voltage we want to, which is represented by this space vector or revolving rotating vector, we want to apply across the motor, and this is the desired voltage vector. Maybe your actual voltage vector is something like this. So therefore, there is an error between the desired voltage vector and actual voltage vector. We will try to study about that error between a desired voltage vector and actual voltage vector which is applied across the motor terminals. Okay, and we will see the effect of different PWM techniques on this error voltage vector. This will be followed by stator flux ripple vector. We will study stator flux ripple vector. What is stator flux ripple vector? Once you have developed, the voltage, error voltage vector, if you integrate this error voltage vector, integration of error voltage vector will give you the flux. Okay, and we know that flux in an induction motor is directly proportional to current. So therefore, the stator flux ripple vector is also, it also represents current ripple vector. I will write here stator flux ripple vector or current ripple vector. Once you know error voltage vector, you integrate that error voltage vector. That basically gives you, integration of error voltage vector gives stator flux ripple vector. But our current, that's stator ripple flux ripple vector, since it is directly proportional to current ripple vector, so stator ripple vector, stator flux ripple vector will be basically representing current ripple vector which is flowing in the windings of induction motor, right? Then we will try to find out RMS line current ripple over a subcycle. Okay, we will take a particular PWM technique and we will find the current ripple vector or stator flux ripple vector, and then we will find RMS value of line current ripple over a subcycle in a PWM technique. Having understood this, we will then try to study influence of switching sequences. I will write here influence of switching sequences on RMS current ripple. RMS current ripple. We have already studied different types of switching sequences like clamping switching sequence. First of all, normal conventional switching sequence, triangle comparison based conventional switching sequence, or space vector based conventional switching sequence. We have also studied triangle comparison based clamping sequence or space vector based clamping sequence. We have also studied double switching clamping sequence or advanced bus clamping type switching sequence. We will try to see what is the effect of various types of these switching sequences on RMS current ripple, right? That will give us a better understanding of different types of PWM techniques, and we will come to know that which PWM technique results in how much of RMS current ripple, okay? And then this will be followed by RMS line current ripple. We'll try to find RMS line current ripple over a sector or a line cycle. I mean complete line cycle. In one line cycle we'll try to find out RMS line current ripple. Okay. Finally, we will study hybrid PWM techniques. Hybrid PWM technique or techniques to reduce the current ripple. This will be a really very interesting topic. We'll see that depending upon the modulation index, for different modulation indexes, we will be using different types of PWM techniques. Like for low modulation index, you may use conventional space vector based PWM technique, and for high modulation indexes, we will be using advanced space vector based advanced bus clamping techniques. That is beneficial, okay? And that means for different modulation indexes, if you are using different PWM techniques which give reduced current ripple, those PWM techniques are called hybrid PWM techniques. So this is our topic of discussion for next maybe 3 to 4 or 4 to 5 lectures, okay? Basically, we will be performing harmonic analysis or analysis of different types of PWM techniques in terms of stator flux ripple or current ripple, and we will see the influence of different switching sequences on RMS current ripple, and then that will give us a better understanding of which type of PWM technique produces how much of current ripple and which is the best PWM technique for a given modulation index which will be applied to control an induction motor. And finally, we will end up with hybrid PWM techniques. That is the combination of different types of PWM techniques for control of an induction motor, right? So let us start with a brief review of various PWM techniques which we have studied over the last couple of modules. A review of pulse width modulation techniques or a review of PWM techniques. The various PWM techniques that we have studied, okay? First PWM technique that we studied was the simple sine triangle PWM technique. Sine triangle PWM technique, or it is also called naturally sampled PWM technique. In literature, you will find this name also given to this PWM technique, that is naturally sampled PWM technique. Okay, so you should not get confused by different names given to the sine triangle PWM technique. We have studied this sine triangle PWM technique probably in module 2 for single phase PWM voltage source inverters, and then we have extended it for 3-phase PWM voltage source inverter. It's simple. We have 3 sinusoidal modulating waves, MR, MY, MB. They are compared with a common high frequency triangular carrier wave, and the gating pulses which are generated by comparison of these 3 modulating waves with high frequency triangular carrier, those gating pulses are applied to the switches of an inverter, and hence that results in generation of 3-phase PWM switched voltage pulses at the output of inverter. And when those 3-phase voltages are applied across the windings of a 3-phase induction motor, they result in the flow of sinusoidal currents. So this sine triangle PWM we have studied in details for single phase version of inverter as well as for three-phase version of inverter. And then we have studied third harmonic injection PWM. Third harmonic injection PWM technique. In third harmonic injection PWM technique, we generated a third harmonic, okay, whose amplitude was given by K times Vm, where Vm is the amplitude of, original modulating wave, which depends upon the modulation index. This third harmonic common mode signal was added to three sinusoidal modulating waves that gave us three modified modulating waves in such a way that for different values of K, for example, for K equal to 1 by 4, we got least distortion in the inverter output voltage, and for K equal to 1 by 6, we got the maximum inverter output voltage. That is, inverter output voltage was increased by about 15.5% as compared to that of that voltage produced by sine triangle PWM technique. The RMS, the peak value of fundamental component of inverter output voltage, which is produced by sine triangle PWM, is increased by about 15.5% if you apply third harmonic injection PWM technique for K equal to 1 by 6. So we have studied both the cases, K equal to 1 by 4 as well as K equal to 1 by 6. Now, as far as the sine triangle PWM technique and third harmonic injection PWM technique is concerned, they are both continuous PWM techniques. They are both the types of continuous PWM techniques, because in both these PWM techniques, the modulating signals, even after they get, for example, in third harmonic injection PWM, your modulating signal is not sinusoidal. It is, after injecting third harmonic, it is distorted, it's non-sinusoidal. But these modulating signals in both the cases are continuous functions of time. And pole voltage is also produced by your inverter, or the average instantaneous average value of pole voltage is produced by inverter in both these modulation methods. They are also continuous function of time. So therefore these two categories, sine triangle PWM and third harmonic injection PWM, they belong to continuous PWM techniques. They are the types of continuous PWM techniques. Okay, this was followed by our discussion with discontinuous PWM techniques or bus clamping PWM techniques. Discontinuous or bus clamping PWM techniques. Bus clamping PWM techniques. And in this discontinuous or bus clamping PWM techniques, we have, for example, studied 60-degree clamp PWM technique using triangle comparison PWM. Okay, how did we achieve 60-degree clamp PWM? How did we achieve 60-degree clamp? We injected a common mode signal. We first of all generated the common mode signal, injected or added that common mode signal to three original sinusoidal modulating signals, and that gave modified modulating signals, which resulted in 60-degree clamp PWM. Okay, now this particular phase leg can be clamped to either positive DC bus in positive half cycle or negative DC bus in negative half cycle in the middle of the waveform, or it can be clamped to the DC bus in first quarter of half cycle or in second quarter of half cycle, depending upon the power factor of load. We have already studied these techniques, the 60-degree clamp PWM technique in detail. Then we have also studied 30-degree clamp PWM technique. 30-degree clamp PWM technique is a type of split clamp PWM technique in which a particular phase leg is not clamped to DC bus continuously for 60 degrees, but it is clamped to DC bus in a split way. Say, first for 30 degrees and then for in one quarter for 30 degrees, in next quarter again for 30 degrees. Now we have also studied continual clamp PWM technique. Continual clamp PWM technique, and in continual, in fact 60-degree clamp PWM technique is a special case of continual clamp PWM technique. We have studied it, and we have also studied split clamp PWM technique. Split clamp PWM techniques, of which 30-degree clamp PWM technique is a special case. Okay, that was about harmonic, this triangle comparison based PWM techniques. Sine triangle or third harmonic injection, or these various types of discontinuous or bus clamp PWM techniques like 60-degree clamp PWM techniques, 30-degree clamp PWM technique, continual clamp PWM techniques, or split clamp PWM techniques. They are all triangle comparison based PWM techniques. Okay, and after this we discussed space vector PWM technique. In fact, I should write here conventional space vector PWM technique. We discussed conventional space vector SV PWM technique. Instead of having three sinusoidal modulating waves or non-sinusoidal modulating waves and comparing them with a high frequency common triangular carrier wave and generating the gating pulses of inverter and producing three-phase inverter output voltages, what we did, we synthesized a rotating reference vector. We assumed that we have a rotating reference vector which is rotating in a circular path. Okay, and when it completes one cycle, it basically, this rotating reference vector basically represents a set of three-phase inverter output voltages. So as your rotating reference vector rotates, the inverter output voltage, three-phase voltages are generated. Okay, by time averaging of nearest three vectors in a particular sector. For example, when your rotating reference vector is in sector 1, the time and as it rotates, the time averaging of null vector and then active vector V1 and active vector V2 produces three-phase output voltages. Similarly, when your reference vector is in sector 2 and as it rotates in sector 2, depending upon the dual timings, it basically generates gating pulses or switching sequence or gating pulses which are stored in the form of a lookup table and fetched and applied to the gating terminals of switches of the inverter, which produces three-phase output voltages. Okay, so this synthesized rotating reference vector basically acts as a reference wave for us. We don't have three modulating reference waves. This rotating reference vector is our reference vector in conventional space vector PWM technique, and it produces the switching sequences in such a way that the inverter produces three-phase sinusoidally varying phase voltages and line voltages. We have studied it in details, and I have also told you that this conventional SV PWM technique, conventional space vector PWM technique, can also be implemented using triangle comparison by generating this type of common mode signal, which is equal to 0.5 M mid. If you remember, we have discussed it in details in one full lecture, and adding this common mode signal to three sinusoidal original modulating waves and modifying the modulating waves like this and comparing those modulating waves with a high frequency triangular carrier wave and generating the gating pulses for switches of inverter, which will produce same results as conventional SV PWM technique. For example, what is the difference between sine triangle PWM technique and conventional space vector based PWM technique? Both of them produce same switching sequences, but in sine triangle PWM techniques, the dual null vector times are not equal. T0 is not equal to T7. Whereas in conventional space vector PWM technique, the two null vectors are equally divided. That's T0 is equal to T7. That gives less harmonic distortion of inverter output voltage in space vector based PWM technique than in sine triangle PWM technique. And secondly, space vector based PWM technique produces about 15.5% higher output voltage than sine triangle PWM technique. Okay. However, this space vector PWM technique can also be implemented using triangle comparison, and that triangle comparison will also give you T0 equal to T7, and inverter output voltage will be raised by about 15.5%. We have already studied that in one of the previous lectures. This was followed by space vector based clamping techniques. For example, we studied space vector based continual clamp PWM technique. Continual clamp PWM technique. And we found that the space vector based continual clamp PWM technique can be very easily implemented by choosing proper switching sequences in different sectors. Okay. We also discussed in details space vector based split clamp PWM techniques. Split clamp PWM techniques, and we have seen that this split clamp PWM technique can also be implemented easily using space vector approach by choosing proper switching sequences in different sectors. Okay. In fact, the switching sequences used in space vector based split clamp PWM techniques are just opposite or reverse to the switching sequences used in space vector based continual clamp PWM techniques. And finally, for our last couple of lectures, we have been discussing advanced bus clamping techniques. For example, we studied advanced continual clamp PWM, advanced continual clamp PWM technique, and we also discussed advanced split clamp PWM technique. Advanced split clamp PWM technique, and instead of using conventional clamping sequence in advanced bus clamping technique, we use double switching clamp sequence, and that resulted in advanced continual clamp and advanced split clamp PWM techniques. We found that using these advanced bus clamping PWM techniques, one phase is clamped to DC bus, another phase switches once, and another third phase switches twice in a subcycle. Okay. So that's all. That is about a review of various PWM techniques which we have been studying over last many lectures. That's about review. Having understood various types of PWM techniques, whether continuous PWM techniques or discontinuous PWM techniques, whether triangle comparison based PWM techniques or space vector based PWM techniques, now it is time to analyze. Time has come to analyze these PWM techniques when we apply them to a particular load. Say our load may be a 3-phase induction motor which we want to control. The question is, out of these dozens of PWM techniques that we have studied, which PWM technique should we apply? Okay. So that will be clear to you as a student only when you analyze these PWM techniques in terms of current ripple or stator flux ripple for different modulation indexes, and you will be able, at the end of the discussion, you'll be able to, or at the end of analysis, deep analysis of these PWM techniques in terms of current ripples, you will be in a better position to choose the best PWM technique or best combination of PWM techniques for controlling your load, or which may be an induction motor. Okay. Now let us discuss first of all maximum fundamental output voltage, which is produced by different PWM techniques. Maximum fundamental output voltage, or which is also called DC bus utilization. Now we have a number of PWM techniques which I have listed just few moments back, which we have already studied in details. Out of these PWM techniques, we will try to see the DC bus utilization. I mean, you have a DC bus, say a 600 volt DC bus or 1000 volt DC bus, we'll see which PWM technique utilize this DC bus better. In other words, when when a particular PWM technique is used, the inverter at its output produces three-phase output voltages. We will see which PWM technique produces higher or maximum output voltage, fundamental output voltage. In other words, we will try to understand the DC bus utilization. Okay. Now, as far as sine triangle comparison based PWM technique is concerned, sine triangle PWM technique is concerned, this sine triangle PWM technique, we have seen it produces peak phase fundamental, peak phase fundamental output voltage. For example, it produces the output phase voltages VRN, VYN, and VBN. And if you find the peak value of fundamental component of a particular phase voltage, say VRN phase voltage, peak value, fundamental component, it produces a peak value of fundamental component of phase voltage which is equal to 0.5 VDC. Okay, probably we have already discussed it while studying sine triangle PWM. So the peak value of fundamental component of phase voltage produced by sine triangle PWM is 0.5 VDC. That means if your DC bus voltage is 1000 volts, it produces 0.5 into 1000, that is 500 volts peak value of fundamental component of phase voltage at its output. Okay. What about this? This is about sine triangle PWM. What about third harmonic injection PWM? Third harmonic injection PWM technique. Third harmonic injection PWM technique produces the peak value of fundamental component of inverter phase voltage, which will be varying from 0.5 VDC to 0.577 VDC. For example, for K equal to 1 by 6, it produces peak value of fundamental component of inverter output phase voltage, which is equal to 0.577 VDC. Okay, and that means it for other values of K, it may produce less than 0.577 VDC. Okay, so that means for K equal to 1 by 6, it produces the maximum output voltage, which we have already studied in details in one of the previous lectures. That means it increases the inverter output voltage by about 15.5%. This arrow shows the inverter output voltage is raised, or it is increased by about 15.5% for K equal to 1 by 6. We have already studied this. After this, we discuss triangle comparison based various types of bus clamping PWM techniques, and also space vector based bus clamping techniques, which are also called discontinuous PWM techniques. Bus clamping or discontinuous PWM techniques. These discontinuous PWM techniques or bus clamping PWM techniques, they also produce inverter output voltage whose peak value of fundamental component of phase voltage is 0.577 VDC. So they also produce greater than sine triangle PWM. They also raise the output voltage by about 15.5%. Okay. And then what about space vector PWM technique? Conventional space vector PWM technique. Conventional space vector PWM technique also produces output voltage, phase voltage, fundamental component 0.577 VDC. That means it also produces about 15.5% higher inverter output voltage as compared with sine triangle PWM technique. And finally, advanced bus clamping PWM techniques or advanced discontinuous PWM techniques. Advanced bus clamping PWM techniques, they also produce higher inverter output voltage 0.577 VDC. So that means apart from sine triangle PWM, which produces a low inverter output voltage, That means which is not able to properly, fully utilize that DC bus voltage. All other PWM techniques, whether they are triangle comparison based PWM techniques or space vector based PWM techniques, they produce about 15.5% higher inverter output voltage. For example, the third harmonic injection PWM technique for K equal to 1 by 6 gives 15.5% higher inverter output voltage. Same is the case with triangle comparison based PWM, bus clamping PWM techniques, conventional space vector PWM techniques, space vector based bus clamping techniques, and advanced bus clamping techniques. They all produce higher inverter output voltage. Now, what is the proof that space vector PWM technique produces higher inverter output voltage? We have not studied it yet. I have been telling you in many lectures in previous lectures, that space vector PWM technique raises the inverter output voltage by about 15.5%. But I have not proved it. Let me try to prove it. For that purpose, if I draw the space vector diagram, for example, this is my vector 1 with switching sequence plus minus minus. This is active vector 2 with switching sequence plus plus minus. This is active vector 3 with switching sequence minus plus minus. Then this is active vector 4 with switching sequence minus plus plus. Active vector 5 with switching sequence minus minus plus, and active vector 6 with switching sequence plus minus plus, and then we have two null vectors, 0 with switching sequence minus minus minus, and 7 with switching sequence plus plus plus. When we join the tips of these active vectors, it gives us a regular hexagon. So this is the shape of a regular hexagon. And as far as reference vector is concerned, the reference rotating vector will be rotating within this hexagon, and it will be tracing a circular trajectory. It will be rotating a circular path. What is the maximum length of this rotating reference vector? Let me tell you the length of rotating reference vector, Vref. It represents the modulation index. Larger the length of rotating reference vector, larger will be the inverter output voltage. I told you that for sinusoidal output voltages, without going into overmodulation, the maximum length of inverter output voltage or the maximum length of reference vector should be, within this hexagon. I mean, this can be the maximum length of the reference vector, Vref. It cannot go beyond this. And if it goes beyond this, beyond the hexagon, then that is overmodulation. And in one of the modules, in one of the future lectures, we'll try to study overmodulation also using space vector approach. And here modulation index will be, almost unity. Modulation index will be unity because this is the maximum length of rotating reference vector. Now, when this rotating reference vector is just touching the side of hexagon, it is, tracing a circular path like this. As it rotates, it will be rotating in a circular path like this. This is the path. This is how it rotates. So that means if it is here now, okay, and this angle is 30 degrees. When it is aligned along vector 1, what will be its maximum length? Its maximum length will be here. Because if its maximum length is here, then it will go outside the circle, outside the hexagon, and that is overmodulation. So therefore, if you don't want your inverter to be operating in overmodulation mode, it should track this circular path. And for this circular path, the maximum length of reference vector, this is your reference vector Vref. This is maximum length, is when it touches the side of the hexagon here in the middle. And when it traces the circular path, it's like this. So that means when your reference vector is not here, it is along active vector 1. This is the maximum length of, reference vector. Okay. Now, what is maximum Vref? You can very easily find maximum reference voltage vector. Okay, maximum this rotating reference vector. See, this is base, this is hypotenuse. What is base by hypotenuse? Base by hypotenuse is cos theta, and therefore what is base? This is the maximum length of rotating reference vector. Base is Vref into cos theta. VDC into cos theta. So it is VDC cos theta, and here theta is 30 degrees. VDC cos 30 degrees. And what is cos 30 degrees? That is root 3 by 2, or that is 0.866. So therefore Vref maximum reference vector is 0.866 VDC, right? So if your maximum rotating reference vector is 0.866 VDC, so therefore what will be the maximum value of peak value of fundamental component of voltage? V phase fundamental component maximum value. What is the maximum value of peak value of, or what is the peak value of fundamental component of phase voltage? That is given by, from 6-step inverter. We already know from 6-step operation, the inverter output voltage is 1 by 3, 2 by 3 VDC, then 1 by 3, then minus 1 by 3, then minus 2 by 3, and like this. And maximum value is 2 by 3 VDC. Okay, so in this case, it will be 2 by 3 into Vref. That is 2 by 3 into what is Vref? Vref is 0.866 VDC. And you will find that peak value of fundamental component of phase voltage for maximum Vref will be 2 by 3 into Vref. It is Vref max. Vref max is 0.866 VDC. Substitute it here. Multiply it with 2 by 3. So this will be 0.577 VDC. Whereas what is the peak value of fundamental component of phase voltage produced by sine triangle PWM? Just few moments back I told you that it's only 0.5 VDC. But in space vector PWM, for largest maximum reference vector length, that is maximum modulation index, peak value of fundamental component of phase voltage, we have proved it is not 0.5 VDC, it's 0.577 VDC. That means it raises the inverter output voltage by 15.5%. So that is the proof that space vector PWM, when it is compared with sine triangle PWM, for maximum modulation index, that's modulation index equal to 1, it raises the inverter output voltage by about 15.5%. The peak value of fundamental component of phase voltage produced by sine triangle PWM is only 0.5 VDC, whereas it is 0.577 VDC produced by space vector PWM. And therefore, the maximum length of Vref is the radius of inscribed circle. This inscribed circle means this circle which is within the regular hexagon, and its radius is the maximum value of Vref. So maximum Vref is nothing but it is the radius of this inscribed circle, and when it is in the radius of inscribed circle, that is the maximum modulation index in conventional space vector based PWM. And for maximum Vref, the inverter produces the output voltage, peak value of fundamental component of phase voltage, 0.577 VDC, which is about 15.5% of that produced by sine triangle PWM. Right? That means space vector PWM gives better utilization of DC bus as compared to sine triangle PWM technique. Now let us come to our main topic of discussion, that is harmonic spectrum of different types of PWM techniques. First of all, we will consider sine triangle PWM technique. I will write here harmonic spectrum of sine triangle PWM. Sine triangle PWM technique. We will start with sine triangle PWM technique, and we will try to find out harmonic spectrum. Let us assume that Fc is carrier frequency, which may be 5 kHz, 10 kHz, 20 kHz, or more than that. Okay, it is the frequency of high frequency triangular carrier wave, and this Fc carrier frequency in sine triangle PWM represents your switching frequency. And for sine triangle PWM, your switching frequency is same as carrier frequency. Now, when inverter produces output voltage, you apply the Fourier series to that output voltage. Inverter output voltage is, like this, something like this. It comprises of fundamental component and harmonic components. But there will be no lower order harmonics because of this PWM technique. We know there will be no 5th harmonic, no 7th harmonic, no 11th harmonic, no 13th harmonic. The most predominant harmonic will be around the carrier frequency and its sidebands. Then 2 times carrier frequency and sidebands. Then 3 times carrier frequency and sidebands, and so on. We have already discussed it while discussing sine triangle PWM in module 2 itself, or module 3 itself. In fact, in module 2 itself. So for example, this axis is frequency axis and this axis is amplitude of phase voltage, peak value of inverter output voltage, phase voltage. For a for f equal to 1.0, 1.0 means fundamental frequency. When frequency is fundamental frequency, which may be 50 Hertz, 40 Hertz or 60 Hertz, is the frequency of modulating wave. So it's also called modulating frequency, the frequency which is applied across induction motor winding, frequency of the voltage which is applied across induction motor winding. And for this, f equal to 1.0 fundamental frequency, inverter output voltage will have maximum amplitude. This may be 0.7, 0.8, 1, depending upon the modulation index. And then there will be no 3rd harmonic, no 5th harmonic, no 7th harmonic. There will be no lower order harmonics. The first harmonic will appear around carrier frequency Fc. If your carrier frequency is 5 kilohertz, okay, so first harmonic will appear at 5 kilohertz. What is this? This is 50 hertz. Fundamental is at 50 hertz and first harmonic is at 5 kilohertz. And what is the ratio? Ratio is 1:100. So this is 100 times than this. So that's why I have put a break here. Break means that this is quite far away from this. Since I don't have space here, I represent it by this break. Then there will be side bands around this. Side bands like this. Okay. Then the next predominant harmonic will be around 2 times switching frequency, 2 times carrier frequency, 2 Fc. We will not have any harmonic at 2 Fc, but we will have its side bands like this. Then we will have 3 Fc, 3 times carrier frequency and its side bands like this. Then we will have 4 times Fc and small side bands like this, and so on. So therefore, when you perform the harmonic analysis or Fourier analysis of inverter output voltage, you find that inverter output voltage comprises of fundamental component, which is at modulating frequency or fundamental frequency F1, and harmonic frequency components. Harmonic frequency components. And those harmonic frequency components are as, number 1, the most predominant harmonic will be around switching frequency or carrier frequency Fc. And then Fc plus minus sidebands 2F1, then Fc plus minus 4F1, and so on. If you remember, I told you that it is given by JFC plus minus K, where for J equal to 1, I mean if J is odd, K will be even, K will be 2, 4, and for J equal to 2 even, K will be odd, 1, 3, so on. We have already discussed it in module 2 itself when we were discussing single phase PWM voltage source inverters. your most predominant harmonic will be around switching frequency. If your switching frequency is 20 kilohertz, so your first harmonic will be around 20 kilohertz and its sidebands. Now, as far as its sidebands are concerned, for j equal to 1, sideband is for j equal to 1, it is fc plus my, what will be k? K will be 2 plus minus 2 f1. This is k into f1. Then it will be, next sideband will be fc, what will be k? K will be 4, fc plus minus 4 f1. So that's what I have written here, fc plus minus 2 f1, fc plus minus 4 f1, fc plus minus 6 f1, and so on. So this is fc plus 2 f1, fc minus 2 f1, fc plus 4 f1, fc minus 4 f1, and so on. And this is called first sideband. This is called, I will write here, these are called first sidebands or first sideband. Now my next most predominant harmonic will be 2fc, around 2fc sidebands. I have already told you that there will be no harmonics around even switching frequency, 2fc, 4fc, but their sidebands will be there. So therefore I will have 2fc. So when, now in this case, when j is equal to 2, it will be 2fc plus minus k will be 1 plus minus f1, and then 2fc plus minus k3, that is 3f1, and so on. So it is 2fc plus minus f1 sidebands, 2fc plus minus 3f1, and so on. This is called second sideband. Okay. Then we have next harmonic will be around 3 times the switching frequency and its sidebands. So 3fc and sidebands, that is 3fc plus minus 2f1 and 3fc plus minus 4f1, and so on. This is called third sideband. And then we will have sidebands around 4 times switching frequency, that is 4fc plus minus f1, 4fc plus minus 3f1, and so on. This is called fourth sideband. And so on. Now, as far as third sideband and fourth sidebands are concerned, as you go towards higher harmonic frequencies, high switching frequency, the amplitude is very, very small. It is negligible. So therefore, we don't consider the harmonics at 3 times switching frequency, at 4 times switching frequency, and we don't consider their sidebands. We neglect them. So what are the most significant harmonic amplitudes? The amplitude of harmonic around switching frequency fc or carrier frequency fc and its sidebands, you can see they have a significant amplitude. Similarly, the sidebands around 2 times carrier frequency or 2 times switching frequency, they are also significant, but these are 3fc, 4fc, they are negligible, so we will not consider them. So therefore, our main concern will be first sideband and second sidebands. Now you can clearly see that first sidebands are significant. Second sidebands are also significant. But the reactance offered to the current because of the voltages around fc and its sidebands and around sidebands of 2fc, the reactance of the motor will be very, very large. And since the reactance of motor at very high, for example, if your switching frequency is 10 kilohertz, so your first harmonic will be at 10 kilohertz, then 10 kilohertz plus minus fundamental frequency may be 50 hertz, 2 times 50 hertz, then 10 kilohertz plus minus 4 times 50 hertz, and so on. Similarly, here your harmonic will be 2fc. 2fc means 20 kilohertz ke sidebands, that's 20 kilohertz plus minus 50 hertz, then 20 kilohertz plus minus 3 into 50 hertz, and so on. So this switching frequency and the harmonics at switching frequency 10 kilohertz and sidebands, the frequency is very high. Similarly, the sidebands around 2 Fc, very high frequency. And at very high frequency, when these harmonic voltages are applied across induction motor windings, they result in the flow of harmonic currents. But since these harmonic currents are at very high switching frequency, the reactance offered by induction motor winding for these high harmonic frequency currents is very, very large. So therefore, induction motor will result in negligibly small harmonic currents. So our harmonic currents, even though the harmonic voltages are, significant, harmonic voltage around Fc and its sidebands, and harmonic voltage around sidebands to Fc, they are significant, but the currents, because of these harmonic voltages, since these harmonic voltages are at very high switching frequency, the harmonic currents are negligibly small. So therefore, almost sinusoidal current will be flowing through induction motor winding. Okay, to understand it in a better way, we will try to draw the harmonic model of an induction motor. Let me draw harmonic model of an induction motor. First of all, it has fundamental model, and then it has harmonic model. For example, if you draw fundamental model means model of induction motor when 50 Hertz fundamental component is applied to it. Fundamental model will be something like this. This is the fundamental model. Fundamental voltage V1 is applied. It results in fundamental current IS, so stator current IS1, rotor current R1, and this will be magnetizing current IM. This is stator resistance RS, this is stator inductance LS, this is rotor reactance inductance LR, and this is rotor resistance RR by S, where S is the slip of induction motor. This is the model of three-phase induction motor on per phase basis, or model of induction motor at fundamental frequency component is applied to it. Because our inverter output voltage is PWM voltage, it has fundamental component and it has harmonic components around switching frequency and multiples of switching frequency and their sidebands we have seen just few moments back. So when fundamental component of voltage is applied, this is the fundamental model of induction motor. And what about harmonic model of induction motor? Harmonic model of induction motor will be something like this. The harmonic voltage is now applied. We don't apply fundamental voltage, we apply now harmonic voltage, Vn. And it results in the flow of harmonic current In. So something like this. This is stator resistance Rs, this is stator inductance Ls, this is magnetizing inductance Lm, this is rotor inductance Lr, and this is rotor resistance Rr by S at harmonic frequencies. See, induction motor, if it is running at a frequency determined by fundamental frequency, that corresponding to 50 Hertz, but harmonic frequency is very high. For example, harmonic frequency may be 10 kilohertz. So therefore, at harmonic frequency, the slip is nearly equal to 1. So therefore, Rs by 1 is Rr by 1 is Rr. So therefore, this rotor resistance is Rr itself. Okay. Now, your induction motor comprises of inductances and resistances, stator resistance and rotor resistance, and stator inductance and rotor inductance and magnetizing inductance. Now, as far as these inductances or reactances are concerned, they are very, very high at harmonic frequencies as compared to resistances. So resistances are negligible. So therefore, this harmonic model of induction motor will get modified like this. It will show only inductances or only reactances. This is Ls, this is Lr, and this is Lm. This is the voltage, harmonic voltage. Yeah. Now, as far as this magnetizing inductance is concerned, it is very high as compared to these inductances, stator and rotor inductances. So it can also be neglected. Its effect can be neglected. So finally, our harmonic model of induction motor becomes something like this. This is the harmonic voltage Vn. This is stator inductance, this is rotor inductance, and harmonic current is In. Now it is very interesting to see that this harmonic current is given by, from this model you can very easily find that this harmonic current, because of harmonic voltage, is given by harmonic voltage by reactance. What is reactance? Omega times Ls plus Lr. The stator reactance is omega Ls, the rotor reactance is omega Lr. So total reactance is omega times Ls plus Lr, but I have to multiply it by N, because see, stator and rotor reactances are omega Ls and omega Lr only for fundamental frequency when N is equal to 1. But for harmonic frequency, the stator inductance is N times Ls, I mean stator reactance, and rotor winding reactance is N times omega Lr. So therefore, the total reactance is N omega times Ls plus Lr, where omega is equal to 2 pi f. F is the fundamental frequency, 2 pi f1. What will be the frequency of harmonic voltage? It will not be omega, it will be N times omega. For example, if harmonic is 1000 harmonic, so N will be then 1000 into omega. So therefore, you can very clearly see that this harmonic current is directly proportional. It's proportional to Vn by N. It's not proportional to Vn only, it's proportional to Vn by N. And for, harmonics, since your harmonics are around switching frequency and multiples of switching frequency, that means this N is very, very large. Because if your switching frequency is 20 kilohertz, so this N will be extremely large. Your first harmonic will be around 20 kilohertz and sidebands. Then sidebands around 20 into 2, 40 kilohertz. So N will be very, very large. Harmonic order will be very, very large. And for very large harmonic order, this harmonic current will be negligibly small. Okay. So therefore, from harmonic model of induction motor, we got this equation that harmonic current, because of harmonic voltage Vn is In is equal to Vn by N omega times Ls plus Lr, and therefore harmonic current is proportional to Vn by N. So this gives us a quantity which is called weighted Thd, and this weighted Thd is the weighted Thd of voltage. It is given by this expression, under root of summation Vn by N square by V1. So we normalize it with respect to fundamental component of voltage. What is the, generally you must have studied in power electronics, basic power electronics, the Thd of voltage, Thd V is given by summation, Vn square by V1, like this. But this is not, I am not writing Thd of voltage, I am writing weighted Thd of voltage. Weighted Thd of voltage is summation Vn by N whole square under root of divided by V1. Okay, so therefore, since we have just few moments back, we have found that the harmonic current is proportional to Vn by N. So therefore, this weighted Thd actually gives us an idea about the harmonic currents. What is the harmonic current content in induction motor winding? Okay. So therefore, that's why it's called weighted Thd. It gives us the weightage of harmonic current flowing in the induction motor because of harmonic voltages. Okay, and if you find Thd of the current, separately, if you find Thd of the current, that is summation In square under root of summation In square by I1. This is Thd of the current. And this is the weighted Thd of voltage. Weighted Thd of voltage actually gives us an idea about what is the Thd or the harmonic distortion of the voltage in terms of distortion of the current. And if switching frequency is very high, the distortion N will be very large and In will be very, very small. So that means even though actual Thd of the voltage may be very high, but weighted Thd will be very, very small, because this Vn by N basically represents the current, because the current, harmonic current, because of harmonic voltages at high switching frequency, at high value of harmonic order will be extremely small. So in that case, weighted Thd will be very, very small. One more thing you must remember, that when you find the THD of the current, we divide this sum of, square root of sum of harmonic currents, we divide it by fundamental component of the current. And worst case is at no load. Worst case is at no load. Why is worst case at no load? Because at no load, I1, because at no load, NL means no load, I1 will be very, very small. It will be just magnetizing or exciting component. So at no load, THD of the current will be very large. And as you put load on the induction motor, that means as load increases, that means I1 increases, the harmonic, spectrum improves. THD of the current decreases, harmonic spectrum improves. So therefore, whenever you want to find the THD of the current, you can find for worst case, that is at no load. Fine. Now, we have already discussed and we have drawn the harmonic spectrum of, voltage, inverter output voltage for sine triangle modulation. And we have found that weighted THD is given by under root of summation ion by n square divided by V1. And it represents basically the amount of harmonic current in the voltage, in the induction motor winding current. And we have found that this weighted THD will be very, very low if you operate your inverter at higher switching frequency, because at higher switching frequency, harmonic order n is very, very large, and ion by n, since n is very large, this ion by n quantity is very, very small, and therefore this weighted THD is also very, very small. Okay, so in other words, even though the first sideband and first sideband and second sideband harmonics, they are significant, but the current because of those harmonics will be insignificant. Okay, we have seen just few moments back. So that completes our discussions on harmonic spectrum for sine triangle PWM. Let us now try to discuss harmonic spectrum for discontinuous or bus clamping PWM. Harmonic spectrum of discontinuous PWM. Discontinuous, which is also called bus clamping PWM. Bus clamping PWM. So it is something like this. Let me draw it from here. This is frequency and this is A for amplitude. This is the amplitude. Fundamental frequency is say 1, and for fundamental frequency the inverter output voltage has maximum value. And then you have first sideband. For first harmonic frequency will be around carrier frequency and its sidebands, which are significant. And then sidebands around 2 times carrier frequency, like this. Then 3 FC and its sidebands. Then sidebands of 4 FC, which are very, very small. So therefore, first sideband and second sideband, we will consider only these, because it is these 2 sidebands, these 2 harmonic frequency components, which result in some small flow of harmonic current. And other higher order harmonics, they will almost produce 0 harmonic current. So we should consider only first sideband and second sideband as far as harmonic voltages are concerned. Now in bus clamping PWM technique, we have already found that one particular phase is clamped to positive DC bus for 60 degrees and negative DC bus for 60 degrees. That means each phase leg or each phase is clamped to DC bus for 120 degrees in a cycle. And when I say in a cycle, cycle means 360 degrees. Out of 360 degrees, each phase, whether it is R phase, Y phase or B phase, each phase is clamped to bus positive and negative DC bus for 120 degrees. Say 60 degrees for positive DC bus and 60 degrees for negative DC bus. So each phase is clamped to DC bus for 120 degrees in a cycle. That is, out of 360 degrees, it's clamped to DC bus for 120 degrees. So that reduces the switching frequency by 1/3. So that means for a carrier frequency, if your carrier frequency is FC, for a carrier frequency of FC, what is effective switching frequency? Effective switching frequency is FSW. FSW means effective switching frequency. It is not equal to FC, it is 2/3 FC, because our each phase is clamped to DC bus for 1/3 of the cycle. 120 degrees out of 360 degrees means 1/3. That means even if my carrier frequency is FC, my effective switching frequency will not be FC, it will be 2/3 FC, because each phase is clamped to DC bus for 1/3 of the cycle. And during that clamping period, there is no switching of the phases, and hence there are no switching power losses, or there is the switching frequency for bus clamping period is 0. So therefore effective switching frequency is 2/3 FC. In other words, from this equation, so I will write it again, effective switching frequency is 2/3 FC. From this, what is carrier frequency? Carrier frequency comes out to be 3/2 effective switching frequency. That means our carrier frequency is 1.5 times switching frequency, or switching frequency is 2/3 of carrier frequency, which means carrier frequency is 1.5 times more. It's 1.5 times switching frequency. So since carrier frequency is 1.5 times switching frequency, or effective switching frequency is only 2/3 of actual carrier frequency, that means switching power losses are less in bus clamping techniques, any type of bus clamping technique, whether it is 60-degree clamp PWM, continual clamp PWM, 30-degree clamp PWM, or split clamp PWM. The effective switching frequency is reduced, and the switching power losses are also reduced. But harmonic spectrum slightly increases. I mean, this may be slightly higher than sine triangle PWM. Slightly higher, not much difference. If their THD is say 3%, here it may be 3.5% or 4%. There is slight, deterioration of harmonic spectrum. So if you increase the carrier frequency, so I will write here switching frequency is equal to carrier frequency for sine triangle PWM. Whereas effective switching frequency is only 2/3 FC for bus clamping or discontinuous PWM. That means for same switching frequency, if you want same switching frequency as in sine triangle PWM, carrier frequency can be raised by 1/5. Carrier frequency can be, I will write here FC, I can make it 3/2 into effective switching frequency. Carrier frequency I can raise by 3/2. That means 3/2 into what is effective switching frequency in terms of carrier frequency. It is 2/3 FC. Okay. Oh, sorry. I can increase carrier frequency. My carrier frequency can be increased by 1.5 times. Try to understand this point. It's very important. For sine triangle PWM, switching frequency is same as carrier frequency. Whereas for discontinuous or bus clamping PWM techniques, whether they are triangle comparison based bus clamping techniques or space vector based bus clamping techniques, our carrier frequency is only 3 by 2 times switching frequency. Our switching frequency is 2 by 3 times carrier frequency. I repeat, for sine triangle PWM, switching frequency is same as carrier frequency, but for bus clamping PWM techniques or discontinuous PWM techniques, the switching frequency is 2 by 3 times Fc. So if you want same switching frequency as in sine triangle PWM, in sine triangle PWM, what is Fc? Fs is equal to Fc. But in bus clamping PWM techniques, it is not Fc, it is 2 by 3 Fc. So if you want same switching frequency as in sine triangle PWM, so your carrier frequency you have to increase by 2 by 3. So that your switching frequency is 2 by 3 Fc into 3 by 2. 3 and 3 goes, 2 and 2 goes. So that means in case of bus clamping PWM technique also, you will have switching frequency same as carrier frequency. But when you increase the carrier frequency by a factor of 3 by 2, which means you increase the carrier frequency of 1.5 times. So for same switching frequency, which is equal to carrier frequency as in sine triangle PWM, you can increase the carrier frequency in bus clamping PWM by 3 by 2 or by a factor of 1.5. Okay, so that the switching frequency in case of bus clamping PWM technique is also equal to Fc, which is same as in sine triangle PWM. And this has some very good effects on harmonic spectrum. What will happen to harmonic spectrum? When you are switching frequency, you are raising your carrier frequency by 3 by 2 times or 1.5 times. Okay, so everything will get shifted towards right by 1.5 times. This will get shifted towards right by 1.5. This will get shifted towards right by 1.5 times. Because now what will be my carrier frequency? My carrier frequency is not Fc. It is 3 by 2 Fc, 1.5 times Fc. So it will shift towards right. What will be my carrier frequency here? 2, it's not 2 Fc, it is 2 into 1.5 Fc. That is equal to 3 Fc. It will also get shifted towards right. So as these, harmonic components, they get shifted towards right 1.5 times. So that means the harmonic voltage will be at higher frequency. Higher the frequency, I have already told you, the harmonic current is Vn by n. Is proportional to Vn by n. And as you are shifting this carrier frequency 1.5 times, you are multiplying it by 1.5 times. So these side bands get shifted towards right. So that means this n further goes on increasing. So that will reduce In further. That means harmonic current will be further reduced. Okay. So therefore, this tells us that discontinuous PWM techniques or bus clamping PWM techniques, they give better harmonic spectrum than sine triangle PWM technique for same switching frequency. Okay. So for example, if you use a switching frequency of 10 kilohertz in sine triangle PWM, let us suppose that THD of the voltage is out, or THD of the current is say 3.5%. Okay. For same effective switching frequency of 10 kilohertz in bus clamping PWM techniques, the THD of the current will be further reduced. It may be only 1.5%. It may be dropped, say, approximately by 2%. This is just an example. Why? Switching frequency in both the cases is same. It's 10 kilohertz here, it's 10 kilohertz here also. But bus clamping PWM technique gives reduced THD or reduced distortion in the current than sine triangle PWM. It's because of this. Because for same switching frequency, for bus clamping PWM technique, you have to increase carrier frequency by a factor of 3 by 2, that's by 1.5. So that increases n, harmonic order. And since In is directly proportional to Vn by n, as n increases, In decreases, and weighted THD also decreases. THD of the current and weighted THD, which is equal to summation Vn by n square under root of by V1, this also decreases. And THD of the current also decreases. So this means bus clamping techniques or discontinuous PWM techniques produce reduced current ripple. Reduced current ripple. So why am I using the word current ripple? Because if you find the sum of all the harmonic currents, RMS value of sum of all harmonic currents, you can call that current ripple. And since bus clamping PWM technique effectively increases the carrier frequency by 1.5 times, shifts everything, all harmonic components towards right. So N increases, IN decreases. So when the when harmonic component of current decreases, that means current ripple decreases, or the inverter produces better harmonic spectrum. Okay, the THD of the current further reduces. So therefore, bus clamping techniques for same switching frequency produce better harmonic spectrum or produce reduced current ripple. So this is very important. This was about harmonic spectrum of discontinuous PWM techniques, whether they are triangle comparison based discontinuous PWM techniques or space vector based discontinuous PWM techniques. And finally, I am going to discuss with you harmonic spectrum of advanced bus clamping techniques. Advanced bus clamping techniques. Harmonic spectrum of advanced bus clamping techniques. We have already studied in last lecture advanced continual clamp PWM technique, advanced 60-degree clamp PWM technique, which is a special case of continual clamp PWM technique. We have also discussed advanced split clamp PWM technique and advanced 30-degree clamp PWM technique, which is a special case of split clamp PWM technique. And we have found that in case of advanced bus clamping PWM technique, there is double switching sequence clamp. Okay, one phase is clamped to positive or negative DC bus, another phase switches once, and the third phase switches twice. So does that mean that effective switching frequency increases? Yes, as compared to normal bus clamping techniques, advanced bus clamping techniques give slightly increased switching frequency. Right? So therefore, the harmonic spectrum will look like this. This is F versus amplitude. This is again fundamental, and then there will be, I will not write here carrier frequency, I will write here average switching frequency, because in advanced bus clamping techniques, your switching frequency is not same as carrier frequency, and it is not 2/3 carrier frequency also. Okay, because one phase switches twice in a subcycle. So you have to find the average switching frequency, which is different from carrier frequency. So FSW here is average switching frequency. So you have to find that average switching frequency in a subcycle or in a cycle. So this is average switching frequency and its sidebands. Then 2 times average switching frequency, okay, sidebands here. And then 3 times average switching frequency and its small sidebands. Then sidebands around 4 times switching frequency, like this. 3FS and 4FS and their sidebands are negligible. So main concern are these. So this is the harmonic spectrum for advanced bus clamping PWM technique. Okay. Now let me tell you here one very important thing. I will write here for conventional space vector PWM techniques. For conventional space vector PWM technique and space vector based bus clamping technique, you should remember that for low modulation indexes, so for low modulation index, second sideband is increased and first sideband is decreased. This is very important, you have to understand that. If you use conventional space vector PWM technique, not advanced bus clamping technique, conventional space vector based PWM technique, and you operate your inverter at low modulation indexes, it has been found through the literature, through research, that at low modulation indexes, you have two. Now our main concern is first sideband and second sideband. Other sidebands are not our concern. It has been found that second sideband increases and first sideband decreases. Now, does it mean that harmonic THD of the voltage will increase? No, THD of the voltage will decrease. Why? Because although second sideband increases, the second sideband is around 2 times switching frequency. And around 2 times switching frequency means that harmonic order is higher. So IN, which is proportional to Vn by n, since harmonic order is higher, IN decreases. And what about first sideband? फर्स्ट साइड बैंड का एम्पलीट्यूड कम हो जाता है, तो इसकी वजह से जो हार्मोनिक करंट है दैट फर्दर डिक्रीजेस. सो देयरफॉर यू गेट लेस करंट रिपल. It produces less current ripple, but this is true at low modulation indexes. At high modulation indexes, first sideband increases and second sideband decreases, and since first sideband increases, इसका हार्मोनिक वोल्टेज का एम्पलीट्यूड इंक्रीज हो जाता है. So and first sideband is not इसमें n ज़्यादा high नहीं है, so IN will also increase. So therefore conventional space vector PWM technique is not suitable for higher modulation indexes as far as current ripple is concerned. It is suitable for low modulation indexes. Okay. On the other hand, if you see advanced bus clamping technique, advanced bus clamping techniques, advanced bus clamping techniques, which are of course space vector based bus clamping techniques, produce higher second sideband at higher modulation indexes and lower first sideband. I mean, if you now consider bus clamping technique also results in increase in second sideband and decrease in first sideband, but not at low modulation index, at higher modulation index. So therefore, if you operate your inverter at high modulation index and you use advanced bus clamping techniques, it increases second sideband and decreases first sideband. Since first sideband is decreased, IN decreases. And since second sideband is increased, but second sideband higher switching, double the switching frequency पे है, so इसमें N बहुत ज़्यादा है, so IN further decreases. So therefore, this gives reduced current ripple and better harmonic spectrum of current. Reduced current ripple, weighted THD कम आ जाएगा, current THD कम आ जाएगा, reduced current ripple. So this is very important. Therefore, this gives us an idea about hybrid PWM techniques. Hybrid PWM technique. What do we do in hybrid PWM technique? If your inverter is operating at low modulation index, we have just few moments back found that at low modulation index, conventional space vector based PWM technique gives lower weighted THD. So we can operate our inverter with conventional space vector PWM technique. And if your inverter operates at higher modulation indexes, because depending upon your induction motor speed control, you may have to operate induction motor now at higher output voltages, higher output frequencies, so modulation index will increase. So at higher speeds, modulation index increases, and as modulation index increases, the less harmonic current or less current ripple at higher modulation index is produced by advanced bus clamping technique, not conventional space vector based technique. So therefore, at higher modulation indexes, we can switch over from conventional space vector PWM technique to advanced space vector based bus clamping technique, because that gives less reduced current ripple at higher modulation indexes and hence low weighted THD. So this gives us the idea about hybrid PWM technique. We will study this hybrid PWM technique in details in one of the future lectures. So the idea is that at low modulation indexes, conventional space vector PWM technique gives low weighted THD, and at high modulation indexes, advanced bus clamping PWM technique gives low weighted THD. Okay, so with this I will end my today's lecture. So in this today's lecture we have just reviewed various types of PWM techniques which we had already studied in module 2 and module 3 and part of module 4, and we also proved that space vector PWM technique increases the inverter output voltage by about 15.5%. We proved it mathematically today. And then we discussed harmonic spectrum of inverter output voltage for sine triangle PWM, which was aided by harmonic model of induction motor also. And we found that harmonic current is proportional to Vn by N, and we defined a new quantity called weighted Thd. Weighted Thd is actually the Thd of the voltage, but it represents the current ripple in the, it represents the ripple or distortion level in the current. Okay, so less is the distortion level in the current, lesser will be the weighted Thd. And then we discussed harmonic spectrum for bus clamping techniques, and we found that for bus clamping techniques the effective switching frequency is 2 by 3 times the carrier frequency, and if we increase the carrier frequency by 3 by 2 by a factor of 1.5, the switching frequency also increases. It becomes same as in sine triangle PWM. It becomes equal to carrier frequency, and since our carrier frequency is increased by 1.5, so the harmonics are also shifted. They are also increased, their frequency is also increased 1.5 times. That increases n, increase of n decreases in. So that means the ripple in the current or current Thd will further reduce. So that gives us a conclusion. That bus clamping techniques, whether they are triangle comparison based bus clamping techniques or space vector based bus clamping techniques, they result in better harmonic spectrum, or they result in reduced current ripple as compared to sine triangle PWM. Okay, and finally we discussed harmonic spectrum for advanced bus clamping technique, and we ended up with the conclusion that for low modulation indices or low modulation indexes, conventional space vector PWM technique gives low current ripple, because at low modulation indexes, second sideband is higher, first sideband is smaller, and current ripple is less. Whereas at higher modulation indexes, advanced space vector based advanced bus clamping techniques give less current ripple, because at higher modulation indexes they also have higher second sideband and lower first sideband. They produce higher second sideband, lower first sideband, and hence reduce current ripple. And this gives us an idea about hybrid PWM technique. That is, if our inverter is operating at low modulation indexes, it gives us an idea that at low modulation indexes we can go for conventional SVPWM, conventional space vector PWM technique, and at higher modulation indexes we can switch over to space vector based advanced bus clamping techniques for reduced current ripple. So with this I will end my today's lecture. I advise all of you to go through this lecture. In case of any doubts, any queries, please put your queries on the WhatsApp group. Thank you.